Okay, my name is Derek Wayne, and I'm going to be doing the Fluent Project, a laminar flow over a flat
flow.
plate.
It does not do
So we're going to
so
get
different
started
parts of the
here
simulation using
with
ANSYS Fluent is shown here. So
Okay,
as you
there we
see,
go.
we can generate geometry, we can mesh the geometry, we set up once the forward I want module one flat the keys, pick things. For example, design modular geometry. It is going to open a new
Just make
package
sure
for me,
this is
which I will be using to generate the model. So since this will be a 2D geometry, I click on the Z-axis. That will generate a 2D plane on XY plane. I would like to change some settings. I want to see a 2D grid with the snaps, major grids.
And some of the settings in sketching. It's going to get 2 major grid shown in 2D and snap.
That I want to see is, let's say, 0.1
Make sure the
meter.
are in meter. Yep.
And I would like to also have 10 steps in a major space grid. Okay, that generates a grid for me. Now I go to draw. I am going to draw a rectangle, which essentially provides us with the entire solution domain. So I click here and then here, just roughly.
Alright, I'm going to draw rectangle. It's not showing up odd, but still should be okay. So just make a front rectangle like that.
Then I should assign some dimensions here. So when we do a 2D geometry, anything on the x-axis will be the work on the 2D geometry. The work will be done on an XY plane. So now what we have is this configuration, the solution domain. So the bottom line here will be our plate, while everything you see.
Actually, here. The length has to be 1 meter.
Here is going to be the air that's going to be simulated, and the left side is one boundary, right side is the other boundary, and top surface is my third boundary. So let's assign dimensions. So if I go to dimensions and click on horizontal, then I can click here, or it's better to just click here.
Okay, we'll just make the height here 0.2 meters. It's fine. Or 0.5 meters. Oh, jeez. There we go. Zoom on this. Looks a lot nicer.
Is a sketch. Now in the next step, I'm going to, so if I open this, we have a sketch. This is our sketch. I will be clicking on.
And we're going to go to modeling. Here is our sketch right here.
Concept, and we want to generate a surface from a sketch. So I click on sketch, surface from a sketch, and I select this. I click on apply under base objects, and then click on generate up here.
There you go.
When I do that, the software has generated a surface for me. So what you see in gray here is actually the air that's going to be simulated. The bottom boundary here is my plate. The left boundary is where the flow is going to be entering. So for example, we know that the velocity is constant here. On the over what we want. So if we cannot really use this mesh, although it's the default of the software because it does not have characteristics that we want. For example, we know that near a solid boundary there will be a huge gradient of velocity, very sharp changes of velocity here. So we want to have more grid points near the surface because that includes the high gradients. Therefore, we need to modify that. So I can click on mesh and go to insert.
Okay, there we go.
And then first I assign a face meshing so that I can click here on this geometry that enables me to select this face actually. Click here and apply, and I can generate mesh again. Still not that much good, but the lines are now very straight. I start with one of them. Let's go to sizing. I clicked on mesh, right click on mesh, then clicked on sizing. Then up here I have this icon that helps me select an edge. So click on edge, and while I push control bottom, I select top and bottom surfaces, or top and bottom lines basically, and then click apply here. Now I have selected both of these boundaries. Now on this information side here, I can change various things that will help me control the number of grid points. For example, I want to have control over number of divisions. So I click here, number of divisions, instead of 1, I select 50.
50.
And I select and I change the behavior from soft to hard because I want this to be a hard requirement. And
Right here, capture curvature is gonna be no, so I can change the behavior from soft to hard like that.
then again I can generate mesh.
All right, I'll generate this.
And if you click on this mesh icon, it's going to actually show you the mesh. There are of course more grid points in both directions, but still it's not giving me the clustering of nodes near the solid boundary that I really want. So again, right clicking on the mesh, insert sizing. This time I only select the left surface and click apply. Then I come here and change the type from element size to number of divisions. And I would like to have 60 divisions here. I want the behavior to be hard.
For the sizing, edge sizing again, I'm going to do this side and this side here. Apply. Number of divisions.
Click on generate mesh, and then that will.
And I'm just going to do this side. Number of divisions. Do 60 for this. Capture curvature. We want no behavior to be hard. And we do want bias, because it's going to be the bottom, it's going to be more focused down there. Bias factor, we'll do 70. And then we want reverse bias on this side, so flat plate will have the most. Oh. That's alright, now it's matching on both sides. There we go. And then generates. Should be good here. Take a look at the mesh. Perfect. So it's more focused on the bottom where the top of our plate is here.
Fix it, and now I have more clustered mesh here in the surface. Now again, I click on generate mesh. It takes very quickly to generate this mesh because it's very easy. Now this is a pretty good mesh for my configuration, because if I zoom in here, you'll see that there are very small grid points near the surface, and the grids are kind of grow in size as the gradient of velocity is actually reducing. So at this point, I've done my mesh. In the next step, before I proceed to defining the simulation or going to the next step, I have to assign some names. So in order to do that, I first start with selecting the surface, the whole surface. I right click on it. I first clicked on the icon that lets me select the surface, then on the surface, and then right click. Then I go down here and find create name selection. Create name selection is a way that we kind of tag different parts of a model. These tags will later be used in the simulation. So it's a good idea to do a better job of tag. I'm going to call this air flow,
And we'll just do
and click OK. Name selections will appear here. So if you click on it, it's telling me, okay, you assigned airflow to the whole surface. Now I click on the edge controller up here, and then I can select the left boundary, right click on it, and go again to the create name selection, and I call this inlet, because I want it to be the inlet of air. Close. I again go ahead, select the right edge, right click, create name selection. That would be outlet. Click OK, so another name selection appears under name selection in the tree. This surface is my plate, so click on the boundary, right click, create name selection. You can just simply call it a plate. Click OK. The top surface, right click, name selection. This one does not really matter much because it's going to be far away from the plate, but just for the heck of it, let's call it far field pressure. And then click OK. You can call it anything you want. Now, at this point, we're ready to save the project again. And once we do that, then we're ready to close this package and move on to the next level, which is initiating the Fluent software and adjusting and setting up our model. So for doing that, sometimes we see a sign like this under mesh, which is telling us there's an update needed. So I right click here and I click on update. It just makes sure the mesh is ready for my solver, which is ANSYS Fluent. It'll take a moment. Once it's done, you will see the check mark. My accuracy. Choose core to the cores. In order to do that, it has one to increase the number of cores that is. It's just going to have light parallel because I know I have capabilities, and increase this number of processes to 8. Then I click on OK.
We're just going to do several processes because my computer can handle it. Should be able to handle it anyways. I'll start that.
click on OK, then the Fluent software will initiate, which is kind of the meat of the computation process. The most important things that you define is
Nice.
here.
Set up the several cores.
So as you see, we can
It's
actually
loading.
take a look at the mesh that is sent to the solver. Note that
Let's give it a
now
second.
our solution domain is divided to computational
Keep it
cells. So we do
chugging.
not really
There we
have
go.
any
Nice. Okay. This is
surface
the way it
anymore. We
looks.
only have a grid which is generated based on that surface.
Ah,
So how do we set up the model now? So on the left,
okay.
there are various ways to do it. You can go on
Here,
the
model.
bar on
Just make
top
sure
of the
this
menus,
is
but I always
flow.
prefer to use
We
the
don't
left
want
tree.
on
So first
omega.
thing to
We
do
want this
usually is to
be,
check. So if you click on check,
laminar flow.
the solver will
There we go.
look into the mesh and make sure everything is correct. It gives you actually some statistics like the minimum x coordinate, y x coordinate, and all that. Since this is a very simple geometry,
Laminar flow.
the check does not take much time, and the information is not very helpful. But in complicated geometry,
this
sometimes
experiment, we
you have
want the
generated
density to be
mesh
1.2,
cells that are negative
and we want the
in volume.
viscosity to be
Yeah, that may sound a little bit funny, but that
So we'll
happens in very
change
complicated
that.
geometry. And when you do click
And
check,
close.
then the software is going to tell you there are negative volumes and you cannot proceed. You have to go back and modify your check. So always click check when you see it done here. It's telling you that it's a good mesh to proceed. You can also report, click on report quality. The report quality will look kind of studies the quality of the mesh. It may give you some warnings or errors if your mesh is too skewed or there are elements that are not useful for the solver. Now, once we're done with general, we're going to do a steady state computation. So we're not changing this here this menu. A pressure-based solver is most of the things we do in CFD, and it's a 2D planar computation. Now, moving on to model, I can model different configuration, different scenarios of our setup is setting up the boundary conditions. Boundary conditions are going to give physical meaning to the math that this software is solving. I start with let's start with the plate. So if I click on plate, it is going to open a window like this. It's a stationary wall with no slip condition, so the flow has zero velocity on the surface of this stationary wall. And that's it. There's no other thermal, radiation, or any other thing that we can change, so we can simply click OK. If I go to the inlet, if I double click on inlet, then it is going to open another type of boundary condition. Automatically, the software understands that inlet is most likely an velocity inlet. If I don't like that choice, I always have the option of changing the type of the boundary.
Just double check that. Yep, 2 meters per second.
Condition, for example, I can click on this menu and it gives me a bunch of different types of boundary conditions that I can assign. I can assign it as a mass flow inlet, outflow, pressure outlets. This velocity is defined. For example, here parallel to the plate. So now I have two other boundaries to deal with. Let's start with the outlet. If I click on outlet, as you see, by default, the software understands that an outlet is most likely a pressure outlet. So it opens a different type of window for me in which I can select the gauge pressure. The gauge pressure of the local value of gauge pressure, basically. So keep that, deal with that. And this simple configuration, you do not expect to have that. So we don't worry about it. We click on OK, or the top boundary. So again, I click on that. By default, it is selected as pressure far field. I don't like this type because I think it's easier for the software to work with the symmetry. Symmetry line is just telling the software, okay, just mirror what you see with respect to this boundary, upper boundary. Click on that and make it okay. So the top boundary is now chosen to be a symmetry line. For the interior airflow, there's nothing you need to do. You can just keep it as is. We don't worry about dynamic mesh or reference value at this point. We can proceed to the solution in the methods. Most of the time, you can keep these as default. There are situations we may want to use a different scheme for coupling pressure and velocity, but we keep it as simple algorithm for now. We always work with second order pressure and second order upping momentum equation. So second order is of course more accurate than first order. Clicking on control, these are some constants. At this point, we do not worry about those, so we keep them as is. The thing we want to change is the monitors. So if I click on monitors, I can find the residuals here. Again, double click on residuals, open a different menu for me. And what this menu is, I have control over the accuracy of the solution that I want. So since this is simply a 2D flow with no heat transfer, there are 3 governing
e to
equations. I have the
-6.
continuity equation,
Looks okay
x
on that.
component of velocity and y
Okay.
component of
Just to make
velocity.
our data a bit more
And on the right
accurate
side
or
here,
precise.
more to 10 accurate results. Uh, and at this point, I'm pretty ready
Close
to
this back up.
initialize the run.
So we're gonna
If I click on
initialize now.
initialize or initialization here, a menu will be open
And
under this task
initialize.
page for me. There are
So
two
super
different
quick.
ways of initializing a
Good job,
model. You can
computer.
always do standard
After
initializing.
that, we're gonna do
Uh,
our
and what initialization
calculations.
um,
We're just gonna do
is basically
500
the initial
number of
guess that you
iterations
need in
and
order to
then
solve
calculate.
this set of differential equations. You need to start with something and solve the governing equations iteratively.
It's
You
gonna
will
run
see
pretty
later that
quickly.
the values that you use
Looks like
here
I have people
may,
running
in
on it.
fact, help the convergence of the code, or if your
There you go.
guesses are too
Calculations are complete.
wild or they do not make sense, you the red
Okay,
color,
so the
we are
calculations are
having
all
a
done.
larger velocity.
Let's
Contour
run.
plots are always good tools to have some qualitative idea of what the solution is getting at. Sometimes you can really see that your solution is not correct by
Check out
looking
our
at the plot, but
contour.
let's see if this one makes sense. Well,
Do a contour
clearly I
plot
can see the
for
formation of the
velocity.
boundary layer on top of the plate. So if I zoom, let's say here, I can see that the velocity is 0 on the surface. It slowly
0 on the
increases and
surface
gets to the
and
values that
slowly increases
um,
over here.
are closer to the inlet.
That's fine.
Now, I can
Just
also
make
do
this kind of large, but that's
vector
fine.
analysis. So I can go here, click on vectors,
Let's
then
check out vector
click display.
analysis,
It is going to give me
velocity,
a vector plot.
display,
So smaller vectors here, a larger vector here, which is showing
and
me the direction of velocity here. So same tool, but with different appearance. I can actually increase the size of these arrows. If I just put 5 here, then the shape of the vector plot will change